adder only. Okay, and if we want to add more than 4 bit, if we want to add more than 4 bit, it will be cascading of this 4 bit adder. Okay, so cascading of 4 bit adder only is done if you want 8 bit or 16 bit or 12 bit adder. If you need cascading of 4 bit adder only is done. That is why whenever we talk about adder, we generally take only 4 bit. So now if a 4 bit adder is taken, what do? We add A naught and B naught, we get something called as S naught, and the carry whatever goes to the adjacent bit. Again we add these two and we get next one. Again the next carry goes, and this goes on. So this you people are aware that what happens in this, and this last carry becomes my fifth bit of the last bit becomes my the last carry, means the MSB of the sum becomes the carry. So if I simply take an example, if I simply take an example here, what is happening? 1 plus 1 is 2. So sum becomes 2 and C naught becomes a carry. Then 1 plus 0 becomes a, again sum, 1 becomes your sum, and now you can see that there is no carry generated. Next what you have 1 and 0, again no carry generated. Then last bit is saying 1 plus 1 is 2, 2 means 1 0, 0 will come here, 1 goes as carry which comes here. Okay, so you have seen various cases. The first case is where you are getting a carry generated. A carry is generated, and generally a carry gets generated if both the bits are 1. Then only carry gets generated. So and of these two will tell me whether the carry is getting generated or not. So generation of carry depends upon both the bits. If both the bits are 1, then only carry will be generated. Right? Now, if there is, now if you see in this case, there is neither carry generating, means 1 0 0. Carry is not getting generated and nothing is getting propagated also, means if I have a case in which all the 3 bits are 1, then what happens? You generate a carry. Okay. Now here also another example, 1 1 0. It is just like the first case, but in between this second and third bit you can see that carry is not getting generated. Okay. Now this I am simply giving you a 4-bit addition. Now there are two ways of doing this 4-bit addition. One is carry look ahead adder and one is parallel binary adder. Okay, in your syllabus both are there. Parallel binary adder is also there. So parallel binary adder, what do? We take these two, sum it, carry it. You all know your full adder circuit, right? So we put the 4 full adders. We put 4 full adders. What is your input for your circuit? Input for your circuit is 4 bits of A0, A1, A2, A3 and 4 bits of B0, B1, B2 and B3. And you have these full adder. And what each full adder comprises of? Each full adder comprises of, I will name it because I have 4 full adders. So each full adder comprises of, what it comprises of? How many XOR gate and how many AND gate or OR gate? Somebody should tell me. A full adder has how many XOR gate? You people don't know your full adder? You really don't know, or you don't want to speak up?
Ma'am, I didn't understand how to do that. This one.
Which one? What you are not understanding? Huh?
Ma'am.
Parallel binary adder, ma'am.
You people have done parallel binary adder in your basic electronics?
No, ma'am.
No,
Like,
ma'am.
I don't remember.
You don't remember? None of you remember?
No, I don't think we did parallel binary adder.
Then what did you
We
do?
had only full adder and half adder.
Ma'am, we didn't do, ma'am, parallel
Yes,
binary
ma'am.
add.
Okay, you did not do. Then I will have to teach that also because I was thinking you have done it in. Okay, anyway, you people know full
There'll
adder
be
and half
two
adder?
exor, ma'am.
Huh?
Yes, ma'am.
There'll be two exor.
Huh. Full adder has 2 XOR and how many AND gate?
6.
No, AND gate are only 2. Okay,
Okay.
I will show you. Can you see my circuit? See my screen?
Yes, ma'am.
This is your full adder circuit. Now, do you remember? I hope you remember this circuit at least. Sum is A XOR B XOR C, right? So Si is A XOR B and C is coming here. So sum is A XOR B XOR C, right? And what is your and formula? Sorry, carry formula. Carry is shown here. What is carry? Carry is ORing. What all it is ORing? A XOR B and C as well as AB. So, okay, let me write the equation here so that you people remember. Okay, I am writing the equation of full adder. Okay, and you all know that a full adder, some formula, actually you had implemented it with the decoder, remember? So you had used, so A XOR B XOR C, that is what was shown in the diagram. 2 XOR gate is take 2 XOR gate of 2 input each is XORing A, B and C. Now coming to your circuit with respect to carry. So what is your carry? In the circuit you could see that it was one of the input was A XOR B, which was getting ANDed, with the C input. This is your next Ci plus 1. A XOR B was ANDing with C input and in total it was XORing with the A and B. This is only when you open, you get your min term, terms, whatever. All of you are clear with this full adder circuit at least? Circuit and equation? Full adder you have done and you know the sum, carry, equation and circuit, right?
Yes, ma'am.
Okay. So, parallel binary adder, what does it do? You all know that a full adder is capable of taking 3 input, 3 numbers, 3 binary numbers of 1 bit each. 3 binary numbers of 1 bit each, and it is able to give you sum and carry, right? Now, in your full adder, if I take one full adder, I will show you here. If I take one full adder, it will take input A0, it will take B0, and it can also take your 3 bit. So what is 3 bit? A0, B0, C0. These are the 3 bit. And it gives the 2 output, which is called as sum and carry. This you people know, right? Now, when I talk about adding this 2 numbers of 4 bit each, I need more full adders. Why? Because one full adder is able to add only 3 bits. But here, how many bits I have to add? So many bits I have to add, no? So we connect this full adder in a cascading fashion, the way it is shown in the diagram here. Okay, so the first one is only A0 and B0 and there is no carry. So if I am using a full adder, I will have to show the carry of this is grounded. Instead, I can use one half adder also, which has capability of adding 2 bits only. But a full adder has a capability of adding 3 bits. So to make the circuit more generalized, we use all full adder only. And the first bit, so what FA naught is doing? FA naught is adding A naught and B naught, and carry is grounded. So when you add A naught and B naught, you get 2 output, because full adder will give you 2 output, one sum and one carry. So S naught is taken out here, and carry will go from this to next one. So it goes to next bit. That is, this is LSB, it goes to next bit. So this sum of the first full adder, the output of the first full adder becomes the input of the second full adder. So this C naught goes from the first full adder FA naught to FA1. Now what is your second bit doing? It is adding A1, B1, C naught, and again it will give 2 output, that is sum and carry. So sum comes here and carry goes to next one. So this carry keeps on propagating from LSB towards MSB. So my 4 full adders, FA naught, A naught, B naught, it will add. FA1 will add C naught, A1, B1. FA2 will add C1, A2, B2, and FA3 will add C2, A3, B3. But if it is a 4-bit adder, the carry of the MSB need not go anywhere, and carry of this MSB becomes my MSB of the final answer. So your FA3 C3 comes as the final answer. So what your answer of 2 numbers of 4-bit each, this is your answer. This is your sum of A and B. And what is this A and B? A and B is written here. So this is called as parallel binary adder. Why it is called parallel binary adder? Because all the A and B are fed to this thing parallelly. And it is also called as ripple binary adder, because in this carry goes on rippling from LSB to MSB. So another name of this is ripple carry adder, because carry is getting added here. So that is why it is called as a ripple carry adder. Now is this clear to you? Analyze it and let me know whether it is clear to you or not.
Ma'am, so carry of each adder gets added to the next adder, ma'am.
Yeah, tell me.
Ma'am,
Yes.
so carry of each adder gets added to the next adder. In the
Yes,
5
yes.
Yeah.
Carry of each adder ripples or is connected. The circuit is like this. Carry of
Yes.
each adder goes as the input of the next adder.
Yes, ma'am.
Okay, and the final full adders carry comes out like this. It does not go to anything else. But if you require a 8-bit adder, then we will be using 2 4-bit adder, and then this C3 becomes the input of the first one. Instead of this ground, this C3 will go to the input of the first one, and that is why it is better to provide a full adder as LSB also.
Yes, ma'am.
Okay, so this what you have seen on the screen now is called as parallel binary adder. Now one question I want to ask, if the same circuit I want to use add as a parallel binary subtractor, what will be done? That comes in your lab also, so that is why you should know. Parallel binary subtractor. You all know na, how to subtract. What is the method of subtracting? If I want to do a same A and B, but I want to subtract now, what is done? Tell me. How do you do this? How do you subtract? What is the method of subtracting? If I ask you to use complement method, what do you do? You will have parallel binary adder and subtractor in your exam also, in your lab also, everywhere. So you should know this. See, what is the method of doing subtraction? In subtraction, what do? We take the first number as it is, and we take 2's complement of second number and we add it. Then it becomes a subtraction, right? You know this method? All of you know this method? There are two methods, 1's complement method of subtraction and 2's complement method of subtraction also. So when we do in ICs, we do 2's complement method. And what is the meaning of 2's complement method? We take your first number A, we take 2's complement of second number. And what is the method of taking 2's complement? 2's complement of second number gets added to first number. And what is the method of taking 2's complement? Somebody should tell me. Fast. How do we take? Tell me.
We take 1's complement and add 1 at the LSB.
Yes, right. So we take 1's complement of second number, that is B for me, and we add a 1, and this will give me the A minus B. What I have written here on the screen, what I have written is, if I want to do A minus B, let A be 4-bit or 3-bit or whatever. But if I want to do A minus B, I should take A and add to this. This is 2's complement. This is 2's complement, right? What is 2's complement? 1's complement of B plus 1 is 2's complement. So we can get A minus B with this. Now, can you tell me some change to this circuit itself to make it as parallel binary subtractor? Quickly, if you can tell me. What can be done to this circuit itself? Or what change can be done here so that I can use it for subtraction?
Mom, we use full subtractor.
Okay, see, we do not use full subtractor actually. I want to do the change in this circuit only. I don't want to use full subtractor. Full subtractor means you will start using XNOR gate, no? I want.
Ma'am, I'm not sure, but we can use invert function for B values, and the ground we can give as 1.
Very good. Perfect. This is what we do. Very good. This is actually what happens in the ICs, whatever is available in market. What you can do is this B0, B1, B2 and B3 will go through a NOT gate now. Okay. It will go through a NOT gate, and this NOT gate will make 1's complement of B, right? If I put the NOT gate to all the B0, B1, B2, B3. If I put a NOT gate, it will just do the complement of B. It will not give me 2's complement. It will give me 1's complement, right? But if I want to make 2's complement, I am supposed to add 1. So what she told I can put a 1 here. So that is very right. We can put 1 there and we can make it as 2's complement. So 1's complement of B is done as NOT gate to B, and this 1 can be done by adding here. Anyway, it gets added in LSB, so it can be added there. So this is how parallel binary adder can be converted to subtractor. I want all of you to note this point. Write down 4-bit subtractor requires NOT gate for B0, B1, B2, B3 and 1 added to the FA NOT. Okay, done. Now, if I want to use this circuit for adder, I will have to, I should not use this NOT gate, right? But if I want to use this circuit as subtractor. I should use NOT gate and I should put a 1 here. Can you think of a common circuit? Can you think of a common circuit which can take care of parallel binary adder and subtractor without doing anything? And I want that you can use it as universal adder subtractor. You can use it as universal adder subtractor. So you will have to change this NOT gate to some other gate, and this will be, there will be something called as mode. If I make the mode as 0, it will work as adder. If I make the mode as 1, it will work as subtractor. So can you think of something like that? One of you gave me a very nice answer by telling me this NOT gate and this 1 here. I want a small change again. What I told you to write, I am writing here. NOT gate at B0 to B3 and 1 bit given to carry input of FA0. Okay, so this will make a parallel binary subtractor. Now I am asking you something more. Now I am asking you a circuit which can do adder as well as subtractor. So this is called as parallel adder as well as subtractor. Can you think how to change mode and which gate can be used which will do both the work? Okay, you are not able to think, no problem. I will give you we can use an XOR gate. You all know, na, in XOR gate, if both the inputs are same, one get propagated. If both the input are different, then A XOR B is what? See, this is the circuit of full adder as well as subtractor. So what is happening here? There is something called as mode. You are able to see my full adder subtractor circuit?
Yes, ma'am.
Okay, so see here M is called as mode. M is called as mode. So if M is equal to 0, what will happen? If M is equal to 0, your carry in will be 0 for an adder. And what will happen here? You all know A XOR B. What is the operation of XOR? If a 0 is here and if B is also 0, what you will get here? You will get a 0. Okay, let me show you here just for understanding, better understanding. If I have A and B here, if I make this A as 0, if B is 0, output will be, what will be the output? Because both the inputs are same, output will be 0, right? But if A is 1, then what will happen? A is 0 permanently, okay? A is 0 permanently. Because I made mode as 0, na? So A is 0 permanently. So if B is 0, 0 and 0 XOR will give you 0. And if B is 1, 1 and 0 XOR will give you 1. So can you see that if A is equal to 0, output is same as B. Output is same as B. But for the other case, if I make this A as 1 all the time, if I make A as 1 all the time, when I make mode as 1, then what happens? If B is a 0, and A is 1, both the inputs are different. So output you get a 1, right? And if A is a 1, then this is 1 and this is 1. Output you will get is a 0. Can you see now? If I make A equal to 0, output is same as input. But if I make A equal to 1, output is complement of input. Are you able to observe this? Tell me yes or no.
Yes, ma'am.
If one of the input is 0, output is same as input. If one of the input is 1, output is complement of input. So this is the trick what we use here. Now you can see, if I make mode m equal to 0 here, if I make m equal to 0 here, all this one of the input is 0. And what do you get here? You get here same. You get here B0, you get here B1, you get here B2, you get here B3. And this circuit behaves as an adder. So M equal to 1, mode equal to 0. Mode equal to 0 means this circuit will behave as an 4-bit parallel adder. But if I make this M equal to 1, when I make this M equal to 1, then what happens? This 1 goes as one of the input to these 4 XORs. And then what do you get here? You get here complement of B0, right? You get complement of B1. You get one's complement of B, you get one's complement of B3. If your one of the input is 1 and the same one is also going here, same one is also going as C in 0. So one's complement is taken care by this XOR gate and 2's complement is taken care by this M equal to 1 addition here. So this circuit becomes a circuit of 4-bit adder as well as subtractor with the capability of changing its mode with this M equal to 0 adder, M equal to 1 subtractor. So this is your 4-bit parallel adder subtractor circuit. And you can see this carry is rippling from LSB to MSB. So this is a ripple carry adders and subtractor. Is this ripple carry adder subtractor clear to all of you now? Can I go to look ahead carry adder now? Any doubt in this parallel binary adder and subtractor? Say yes or no so that I can proceed. If you have any doubt, you can tell me that also.